We're good? Okay. Welcome everyone to AI Semiconductor Testing at the Edge. For the next 20 minutes, I'm going to take you on a little journey through the semiconductor test industry, and we'll look at how we're applying AI and machine learning as we move from this pre-AI to post-AI era. Could I get the slides up? Thank you. All right, so our semiconductor industry, semiconductor test industry, is going through this transformation right now, really this digital transformation as we move from Era 3, which was mainly based on the mobile solutions, or the mobile industry, and moving into Era 4, which is the AI era, which we also call the age of convergence. One of the things we want to think about here is the magnitude of the changes that we expect with this era. So just as the internet had a huge impact to PCs and new industries were created and sprung up, we believe the same thing's going to happen with AI and AI inside of semiconductor test. If you look at the graph, you can see that we're forecasted over the next 10 years, so in about a decade's time, reach $1 trillion. And while that is amazing and fantastic, there are two key takeaways that we want to highlight in this graph. The first is, notice the exponential growth rate of the AI era. So we're really literally moving from a linear growth rate into an exponential growth rate. The second is, notice the ebbs and flows, or the ups and downs, the cyclical nature that preceded Era 4 has all but vanished or disappeared. So those are two important takeaways, and the reason for that is because semiconductors have become the new social infrastructure. And that's just another way of saying that semiconductors are in everything that we do in our lives, continuously. I'm going to use the mobile backdrop to sort of carry us through this story. So when we look at the various segments of the mobile, which some of them are shown here, all of these segments are growing. And what this social infrastructure means is that we've kind of reached this critical mass point where we've overcome the cyclical nature of the preceding eras. And so one segment actually fuels and encourages the growth in the other segment. And this has a snowballing effect, which is why you see that exponential growth, and also why you don't see those cyclical natures anymore. So we expect for the foreseeable future for it to remain this way. So this looks like it's going to be the new norm. Now, zooming in to semiconductor test ecosystem. This is a very simplified vision of the back-end process. So after wafers come out of the fab, they have to go through a series of test insertions. In the beginning, they're tested in wafer form. The good die get yielded, that gets packaged, and is tested again in package form or final test form. Those packages often become multi-chip module packages or system-in-a-packages, and they get tested continuously as they traverse down this back-end line. So what that means is there's an inordinate amount of test, but there's also an inordinate amount of data that gets generated throughout that product life cycle. And what AI and machine learning bring to the table is if we can figure out how to utilize that data, we can make some big progress in reaching that $1 trillion mark. So just to describe these briefly, for wafer test, that's actually a micro ecosystem unto itself. So there you need probers, probe cards, and of course the tester. But the equipment changes completely when you move to package test. Now you need handlers, you still need the testers, but now you have load boards and sockets. So a completely new industry services, or completely independent industries can service each of those test insertions. So what that means is our ecosystem is extremely sophisticated and extremely complex. And you can see from some of the items here, we have multiple insertions. We have known good die that come off of the wafer, which get packaged with other known good die. So consider a memory and a PMIC and an ASIC, all separate but then packaged together. You can imagine that if one of those fails once it's packaged, the cost of that is extremely high. So the last thing we want to do is wait until we get to the very end at system level test, where for the mobile, for example, the entire thing is put together and then you boot the phone and it doesn't work. And we've seen stories about that in industry, for example, with the antenna that are misplaced in the phone, or the phone reboots itself when a particular application is run. So these are catastrophic failures that are detrimental to the brand, and we need to fix those, especially as we move to autonomous driving vehicles. It's one thing to have your phone crash, but it's another thing to have your car crash. The other point we want to make about this era is think back on when the internet emerged. At the time, it was thought of as a sort of research and design vehicle for universities. But the companies that embraced that internet, those are the powerhouse companies of today. Those are some of the most successful, richest companies that we have in the world. And we believe the same is going to be true with the AI era. However, because of these complexities, we're going to have to move away from point solutions. The industry itself, so the semiconductor test industry, does a fantastic job and has done a fantastic job of optimizing each and every one of these insertions. As I said, there are micro ecosystems that service that. And they have specialized hardware and specialized software that optimize yield, optimize throughput, optimize efficiency. But what's not done is there's not much of a connection from one insertion to the other insertion. So for example, we don't have data free-flowing from the start of the process to the end of the process, and vice versa. And that puts some strict limitations on the types of quality that we could impose on the system. So if we want to get to self-driving automobiles, for example, the tenet is we need to drive to 0 defects. We used to talk in terms of defects per million, and several years ago we changed to defects per billion, but now it's 0 defects. So how are you going to get to 0 defects? Again, you don't want an autonomous vehicle crashing. That could lead to loss of life, and that's millions and billions of dollars. And the way that we see to do that is we have to start looking at the entire system holistically and optimize it as a whole. So, the self-developed systems that are already optimized in each of those insertions, those are not scalable because you can't connect them so easily together. The data formats are completely different. The way the data is stored, the way the data is managed, they're completely separate, isolated systems. And what that means is it's unscalable. So we're going to have to change that and overcome that in order to apply AI and machine learning to the entire ecosystem. So that's the question that Advantest is answering with its partners and its suppliers. And we know what a little data can do. So we have great optimizations in each of the test insertions, but now we need to change the way we think. What can we do with big data in semiconductor test? I'm going to walk through 3 use cases, and there are dozens of other use cases, and there are many more coming that we don't even know about yet. They haven't been invented. But just with these 3 use cases, we can show that there's a $1 billion impact by applying some of these methodologies in the semiconductor test ecosystem. So the very first one I want to talk about is rebalancing the test. Remember, we just said that each of the insertions is optimized. There's another constraint, and that constraint is we only have so much test budget. In general, as a rule of thumb in our industries, we allow 3% of the overall cost to go towards test. That means from the post-silicon validation all the way to system level test, you have about a 3% budget to spend. So if your quality requirements are increasing, which generally dictates more cost, we can't just arbitrarily, continuously increase the test cost because we'll blow through the budget. So we have to be smarter, we have to be more clever about how we approach the problem. So in this case, I want to draw your attention to the wafer sort 1, 2, final test, and system level test. And what you see there is a visualization of the yield, where the red boxes at the top indicate the failed percentage. So in wafer sort 1, you have that amount of failures, wafer sort 2, that amount, so on and so forth. They're optimized as best they can, but we can do better. Using machine learning and AI and fully connected data flows, we can actually balance the entire thing and stay within that budget. So what does that mean? So in this example, the machine learning AI is actually recommending to increase failures, which is counterintuitive to the person that's responsible for the wafer sort area. So the machine learning is saying, hey, increase your wafer sort failures by 2%, your wafer sort 2 by 2%, and your final test by 2%. So your cost in all 3 of those areas is actually going to go up. But your system level test yield is going to improve by just 1%. So that 1% more than makes up for the additional cost of the failures, again, because you failed earlier. So you failed the devices earlier, you didn't spend all that time and energy and money and only to throw the part away. And it works both ways for failures and for good parts. You can pass earlier. If you know from the AI prediction that the device is highly likely to pass, then you can skip tests as well. So you get a double reward for doing this. And just with this simple example, using mobile numbers today, or mobile volumes today, you save around $30 million a year. Okay, what do we do with all those failures though? Should we throw them all away? In many cases, yes, we're going to have to throw some of those away, but not all of them. So AI and machine learning is very good at predicting performance, right? That's one of its killer app features, is it can predict how that device is going to perform out in the field or at a later stage. So you'll get these clusters, and the machine learning will say, hey, this super high performing cluster, that's your high quality product. Ship that to your automotive customers. But the second cluster, although it still passes, we don't want to ship it into the automotive because the quality requirement is too high, but you can sell this into a tier 2 or a tier 3 market. So in that way, you actually get yield recovery as well. So in this case, in this example, The machine learning is telling the system, take some of those failures, they're not actual hard failures, don't ship them to your tier 1 customer, but you can ship them to your tier 2 customer. And that saves you around $35 million a year. The last one is actually the holy grail. It's the biggest one. And this is really about quality, brand management. This is about your company's reputation. So again, imagine if your mobile phone goes out into the world and it doesn't work, that can cost you tens of millions, hundreds of millions of dollars, and of course a bad reputation. This would be catastrophic if it happens in an automobile because it could lead to loss of life, and now you could be in the billions of dollars in terms of damages. One thing I would say about this is our industry is extremely good at correlating and finding the root cause once the problem is known. So this is key. If the problem is known, meaning we have the customer return and it's come back to us, we can find it. And you see here, we have teams all over the world that work with the labs, take the correlation data, and figure out a series of tests that could be performed earlier that could capture that problem or capture that fault. But then that begs the question, if you can do that, why can't you predict that? Stop it from ever happening in the first place? And the answer is we can do that. If we fully connect and integrate the workflows together, the machine learning algorithm can not only predict what the errors are going to be, it can also then prescribe the solutions or recommendations to prevent that error from ever happening in the first place. So in this example, if we prevent one of those per month, you can see it has a positive $880 million benefit. And now this is just looking at the mobile industry. If you think about automobile industry and some of the other industries, this value is well over $1 billion of impact. But to do that, we have to move from those siloed, isolated, optimized solutions that are just optimized for that single insertion, and we have to move to fully interconnected data paths and let the machine look at all of the data coming from all of the insertions. And when we do that, we're able to employ some of these methods that we just talked about. So, what is needed? How do we do that? So I'm just going to talk about two very important things that Advantest is working on. The first is we have to verticalize the stack. So what does that mean? Each of these test insertions, we call that a test cell. And the test cell is comprised of things like the tester, the handler, the load board, the device, and all the sensors that go along with it. We have to integrate all that data together and be able to run models directly there at the edge so that you can get the most value for those insights immediately. So we've already been doing this for a couple of years, and we have this deployed in production. We call this ACS Edge, Advantest Cloud Solutions Edge. And I'll get into the ACS part here in a minute. But suffice it to say, we have a supercomputer that we can plug into any of those insertions. And it's a direct connection. And that solves the three main requirements to enabling this verticalization. The first is security. So ACS Edge has built-in encryption and security to manage the data at rest and data in movement. The second is the ultra-low latency. Whenever we're testing, again, we only have a 3% budget, so we can't afford to send things to the cloud and wait for an answer. We need to do it right then and immediately. And so having a direct connection solves that problem. And the last thing we do is the reliability. we have our own network because of that direct connection directly to the testers or the test cell. Now we're not dependent on the facilities or the network infrastructure that's already in existence. And so by this, we solve all three of those problems, and again, this can run in production. The second piece, which is a much bigger piece, we have also been working on this for a couple of years, is the horizontal integration. So we just talked about the vertical piece, but we also need to connect all those data feeds across the insertions. But you'll notice here, it's not just across the test insertions. It's also across the fab processing steps. When the wafers go through the fab, each and every process step generates data, and we're tying into those. But we're not stopping there. We're also partnering with the EDA vendors and tying into those data feeds. So now you can get to this truly prescriptive environment where it can not only detect the fault before it occurs, it can actually go back into your design and recommend what to change in the design or what to tweak in the process in order to eliminate the threat from ever occurring. So this is the last slide, and then we can take some questions. Our vision, Advantest vision, is using Advantest Cloud Solutions open solutions ecosystem. And this is important that it's open. As we described earlier, there are a lot of great point solutions that are already in place. They've invested heavily over the last 20 and 30 years in those solutions. We don't want to throw them away. We want to enable those customers, enable that supply chain and partners to be able to take those tools and plug in. So we use open container Docker technology. We use HTTPS. If one customer likes to use Python environment and another likes to use PyTorch and another likes to use Kubernetes, it doesn't matter to us because it's all containerized. So customers can bring their tools, their services, their expertise, containerize it, and deploy across the various insertions and start taking advantage of the AI and machine learning methodologies. So I'll close with, we're on this path over the next 10 years to reach 1 trillion. In order to get there, we're going to have to change the way that we think and employ test methodologies. I suspect that we can actually get there much faster if we adopt these methodologies and implement them much faster. So Advantest is ready for this. Let's get to work, and we're here to help. Thank you.